Hello, hello. Here we are, Chapter 8, Energy, Section 8.6, The Law of Conservation of Energy. It's on page 109 in your textbook if you're following along. And today we're going to use the example of how is mechanical energy conserved. That's a simple example. We're trying to keep things simple. The law of conservation of energy is very simply stated. It just says energy can neither be created nor destroyed. So that means energy goes from one form to another. Here's a list of forms. This is as long of a list as I could make. Lots of words in there. Some of the ones that are familiar are up top. I added even the weird ones like translational. The very bottom, food, that should be familiar. Coal, solar, wind, those are things you see in the news. But we've talked about at least half these. So here's the classic example of how energy is conserved. We start off with a big red apple on a tree. It's up high off the ground, so it has a height. And someday the apple tree is going to let go of the apple and it will fall to the ground. But for now, the apple's up in the tree, and because it's at a height off the ground, it has gravitational potential energy. That's from the height. Do you remember the formula? Potential energy equals mgh, mass times gravity times height. So that apple has some potential energy, and it's just sitting there. And then 1 second it's attached to the tree, and the next second it is not. And at that instant, it starts to fall, and it moves down. And as it moves down, it accelerates due to gravity. So its speed is going up and up and up. The speed is getting faster, let's say. As the object falls, it's going down, so it's losing its height, and it's also losing potential energy. So where does that potential energy go? It goes into the kinetic energy. The apple's going faster, and that's how energy is conserved in this classic example. The potential energy is transformed into kinetic energy as the velocity increases and as the height decreases. If the potential energy is being converted into kinetic energy, then the total mechanical energy of the apple does not change as it falls. The potential energy that the apple loses is gained back as kinetic energy. And once again, the form of energy changes, but the total amount of energy remains the same. And that's an example of the law of conservation of energy in action. Here's another example. Now how do we measure energy? With joules, do you remember that? So if we have 100 joules of electricity coming out of the socket and into the hairdryer, then you have 100 joules coming out. Now it can come out in different forms. There's thermal energy because the air is getting warmed. There's kinetic energy because the air is being pushed really fast from the fans. There's also sound energy. You hear it. It's vibrating, so there's vibrational energy. There's friction inside from the fan spinning. The point is that the 100 joules that go in, you can measure it and find every last joule that's being used by the hairdryer. And it's always the same. Energy is never lost. It's only changed in form. Here's a couple questions. The total mechanical energy of an object is hit pause if you want to take a minute and read through those. The correct answer is D. Kinetic energy plus the potential energy of the object at any instant during its motion. You might have thought C is correct, and C is not wrong. It is the initial kinetic energy plus the initial potential energy. But D is more correct because it's true not just at the initial time, but at any time. Another little question. If an object moves in such a manner as to conserve its total mechanical energy, then, hit pause if you want to read through it. D, the sum of the kinetic energy and the potential energy remains the same throughout its motion. This is a chart that I'm going to ask you to fill out. It's in the homework assignment. It's the first page. I'll talk about it a little bit here first, though. So there's the acrobat you see in the picture on the right. He's standing on top of the pole. And I'm telling you that his potential energy at the top of the pole is 15,000 joules. Because he's standing still, his kinetic energy is 0. And we already learned that the mechanical energy is the sum of PE plus KE. And so his total mechanical energy is also 15,000 joules. So if the total mechanical energy stays the same because of the law of conservation of energy, after he falls down about a quarter of the way, his potential energy is labeled at 11,250 joules. So his kinetic energy is, it's 1/4, 3,750 joules. Halfway down, his potential energy is 7,500 joules, so his kinetic energy is also 7,500 joules. And then all the way down to the bottom, when his potential energy is 0 joules, because in the next instant he lands in the tub of water, then his kinetic energy is the full 15,000 joules. So there is the first column and the third column. Mechanical is always 15,000, and the kinetic energy you can fill in. Then the height. Well, how do you figure out the height? If you look on the worksheet, I give you the equation for potential energy. So when he's standing still on the top of the pole, his potential energy is 15,000 joules. You don't know his height, but you know g, the acceleration due to gravity, and you know his total energy, 15,000 joules. And you know his mass. It's written down on the worksheet also at 75 kilograms. So you have all the variables filled in except for height. So if you solve for height, you can figure out how high he is at each step of the way. The same idea for velocity. The kinetic energy equation is written on the sheet, and it's 1/2 mv squared. So the mass is always 75 kilograms. The energy is what you filled in on the table, and then you can work to solve v. Now that's a little trickier with the math. If you look on the second page of the worksheet, I walk you through that math of solving for velocity when the equation is Ke equals 1/2 mv squared. Okay, on to the next slide. Oh, so this is the second problem in the homework. I have an example. It's a car instead of a little red wagon. The question here says the potential energy is high because they have a high height, and the kinetic energy is low because they're just moving over the hill. And then at the bottom of the hill in point B, because they're so low, the potential energy is low and the kinetic energy is high. That's just reinforcing the point from over here. As the acrobat dives off, the potential energy goes down, the kinetic energy goes up. So where's the velocity going to be the greatest? At the very bottom. So between A and B, it's going to be bigger at B. Where is the object going to have the same speed? That's a good, tricky question. So at any height, at any point where the height is the same, the speed will be the same. Of course, we are assuming that this is a perfectly frictionless system, so the wagon's not slowing down. So if you draw a line across, a horizontal line across, wherever that line hits the curve of the hill, that's going to have the same height, and therefore it's going to have the same speed. That's pretty advanced for right now. This is still introducing the concept on the first day. This is showing some of the math, and I'd like to talk about this to make the math be a little easier. So there's the picture on the right. We have the acrobat at the top, where his potential energy is 15,000 joules, and Ke is 0. That's the initial condition. And the mechanical energy for the initial condition, that's what the Me sub I stands for. Then the Me sub F is final condition. So right before he lands in the bucket of water, his potential energy is 0, but his kinetic energy is the full 15,000 joules. So we know those two things are true. They're equal. And then I can expand the mechanical energy from mechanical energy to potential and kinetic, because mechanical energy equals potential energy and kinetic energy. So that's all I'm doing. I've got the initial condition on the left and the final condition on the right. So what's the potential energy at the initial condition? It's the full 15,000, and the kinetic energy is 0, equals the potential energy at the final is 0, plus the kinetic energy at the final is 15,000 joules. That should have been a capital E. Then I can also substitute one more step. We know that PE equals mgh. That's what we did 2 days ago. So instead of potential energy, I'm writing mgh, the mass times the acceleration due to gravity times the height at the initial condition. Then I can do the same thing for the kinetic energy, 1/2 mv squared. But remember, the kinetic energy initial is 0, and the potential energy final is 0. So I can say that I could simplify that last line into mgh initial equals 1/2 mv squared final, because the other two in the middle are zeros. So I can go on to solve for any one of those variables if I would like. I have the mass, I have g, 10 meters per second squared, and that's how you would solve for the height. So if you don't know the height, you can plug in the m that you know, the g that you know, and the energy on the other side is 15,000 joules, and that's what the homework assignment takes you through. So please go ahead, open up the homework assignment, and have a look at that. But let's finish this slide. Another question. We can skip that question. And then there's the worksheet that comes with that came with this PowerPoint that I grabbed, but I didn't like this worksheet, so I wrote a better one. It's a little more direct and step-by-step. Okay, so please try the homework. Take a picture and send it to me. You can write your answers on a blank sheet of paper. And I tried to put extra little notes in there and make the question numbers all separate so that it's easy for you to just write, the number or the letter on the page, and then show your work and write the answer there. Thank you so much. Bye-bye.